Okay, so today we're continuing on looking at templates, and so this is the third or fourth week that we've spent looking at templates now, and we're still working our way towards how to design custom iterators. And so hopefully we'll make it to custom iterators by Thursday, but today we're looking at type traits. And type traits are a class or a class template that characterize a type. So a type trait is a class or template that characterizes or tells us some information about some other type. They tell us about some parameters or some properties of these types. And so way back on the first lecture of the course, we showed you how to get for numerical limits of doubles or ints, how to get for maximum and minimum values. That numeric limits library was a type trait library. It told us some information about the type. In the case of numeric limits, it told us the minimum or the maximum value. And the way in which this type trait library might look like underneath is it might be a template with a struct called numeric limits, and it has a function called min. And then there's a template specialization for the int version and for a float version and so on and so forth. And the int version relies on actually a C-style macro being defined in the compiler specifications of int max. So there's underscore underscore int capital underscore max is actually a hash-defined C-style macro that the compiler interprets and knows to put in the maximum value for an int. And so the minimum value for an int is actually negative int max minus 1. Don't worry about how the math for that works, just in binary that just works out to work out what the minimum version of max int is. And the same for float, there might be a hash-defined float min. And for all your different types that are numeric, there might be these hash-defined numeric limits defined within the compiler. But the purpose of this, or the point of this, is not so much that there's these hash-defined numeric limits. The purpose is wrapped up in a nice little class, templated class called numeric limits. We can use this as a type trait to find information about a class that we're passing in. And so this was very, very simple. Now, we can then use these type trait libraries to do interesting things. And the interesting thing that we're looking at here is, again, let's start down at the bottom. Let's look at main. Main has three different arrays. One is an int array, one is an unsigned int array, and one is a float array. And if I just bring it up, so find max is what I'm looking for. Okay, so if I bring up this findmax.cpp file, okay, well, this is the same code on both screens now. Okay, what we want to do is we want to be able to find the maximum value in each of these arrays. So int, unsigned int, and float arrays. We want to find maximum value. Now, forget about the rest of the code on the screen. What is the standard approach for finding the maximum value in a container or in an array? How would you find the maximum value in an array?
Check every element and pull it from the max.
Yeah, you've got to check every. Okay, so you've got to check every element and find the max. But how do you do that? What's the algorithm for how you do that? Assume the first one's the max. And then go from there. Okay, yeah, let's assume for the first one's the max, and then you could go from there. How else might you do it? Yeah, I mean, that's pretty straightforward, okay?
Sort the array and then find the last element.
Oh, you can sort for array and find last element and stuff like that, okay? But what we might want to do is we might want to have some sort of generic way of being able to do this. And so what we have up the top of here is an algorithm that uses type traits to do this. And so what you might have is you might have a variable called current largest, and you might have originally set that to 0 or something like that and keep it increasing, but 0 isn't going to work if you're dealing with ints. Because maybe your container of ints is all negative numbers, so setting it to 0 isn't going to work. Maybe you have a container or a collection, a custom type, where for some reason for minimum value might be 10 and the maximum value might be 100 or something like that. So you can't just assume that you have a 0 or a -1 or some special magic number that tells you where to start. And so this type traits example that you're seeing on the left-hand screen is using the numeric limits of type t, which is passed into this function find max, to start this loop rolling. And once you have this loop going, yes, you just do the standard comparison of if something's something's greater than the current minimum or maximum value, keep shifting along, okay? But it's using the type traits library to facilitate this. Or in this case, it's using the type trait that we just defined on the previous slide, but in real life, you'd use limits.h, or hash include limits, to do this. So can everyone see how this template's working so far? This is the easy stuff, okay? Here's another example. This is a type trait for figuring out if a parameter or a type is void. We have a struct is void, and by default, it's false. In the case that the type is actually a void type, then it's true. And so we can print out is void, val. We've got vowels, either that vowel or that vowel. So this is either going to print out true or false, depending if the type is void or not void. Is void int? False. Int isn't a void type. Int is a int type. Is void void? Now remember that void is a type. It's kind of a bit of a useless type, but void is a type. Actually, it's not completely useless because we use it all the time to return from functions, because functions always have to return something, and so we return void. Often when we don't want the function to return anything. Void is this magical type, it is a type, but it's a magical type, it does nothing. But sometimes we don't want things to be void. So you could use this in the case of, say, you were using some auto type declarations or something like that, and it was complex. You had an iterator or function, might be overloaded, might be returning a couple of different types, you're not quite sure what's happening with it. And so you're feeding auto into the result, and you want to know if this auto variable you've declared is void. You can use this type trait to do so. So actually, before I go to the next slide, I want you guys to work out what the next slide is. The next slide has a type trait for working out if something is a pointer or not a pointer. What would the type trait look like? So you might be able to use that is void as a starter, but what would the type trait for is pointer look like? Anyone know? Well, first of all, how many pieces do you think it's going to have? One. You only think it's going to have one. Okay, it's going to have two. Yes, it's going to definitely have two. Okay, because its pointer is either going to be a true or false. Okay. What's the false case? Yeah, it's not a pointer, but how do you know if it's a false case? Like, look at the templates up the top of here. Okay. Look at the templates. The reason why I'm pausing on this is there is a few questions on this type of stuff in the exam. So there's a reason why I'm pausing on this a little bit. You won't be asked in the exam to go write this. What you will be asked in the exam is a question that might look quite a lot like this, and ask you What's the output of this? Does this compile? Does this make sense? Do you understand what's being called at which point? So maybe we'll back up a second. First of all, does everyone understand this slide? Everyone understand what's happening on this slide? Okay, so let's talk about the case whereabouts we're trying to do is pointer. It's actually really simple, okay? But is pointer, first of all, just is void gets replaced by is pointer. The second part is basically the same. If it's just a standard type, then clearly, if it's just type T, clearly it's false. It's not a pointer. The difference for is pointer is for template specialization. Rather than void in there, we need a template specialization for pointer types. And again, this should be revision because we talked about this a few weeks ago. This template down here is a full specialization. Why is it a full specialization? Can someone tell me? Why is this?
All of the parameters being initialized.
Well, it's not all the parameters have to be initialized, but all the parameters have to be set to a particular type. So this is a full specialization because void is a type. And so this is the template specialization on a particular strict type. Okay? A partial specialization, if you remember, can still be a template, but it's not necessarily a strict type. It can just be part of the types can be set, or it can either have, I'm trying to hand wave a little bit because again I don't want to give answer away, but it can have some sort of property of the particular types, which is kind of what we're getting into with type traits. So there's no strict pointer type, singular. There are many pointer types, because basically for every type that we have, we can have a pointer type version of it. And a pointer type version and a normal type are different. In the same way we can have an int and an int pointer, they're two different types. So we've determined so far that is pointer is going to be just looking basically the same as that. But the second part down here is not going to be a full template specialization, it's going to be a partial template specialization. So if I jump to my answer, T star, simple. When you see it, it's easy, right? So the only difference between that previous slide and this next slide, the previous slide had void, which was a full type. And this next slide just had T star, which is a partial specialization. Okay? But is pointer int star will return true. Is pointer int, that's not a pointer, it will return false. And so again, these template specializations can tell us some interesting information about types. So where might we use this? Oh, I'm going to jump 2 slides. Where might we use this? Well, here's a program I wrote up on Friday, which uses the type traits actually defined in the standard library for determining if something is a number or not a number. And the reason why I'm giving you this example is actually because last week's tutorial, remember we had the variadic functions? And we're trying to determine if something was a number or not a number and print it out. Here is how you might do it for many different types. We have this type trait library, which returns true if something's an integral, so i.e. it's an int, a long, a short, something like that. Or it's a floating point number. Now, floating point number, again, you can have a float, you can have a double, you can have a long double. And so we can test if these things are a number or not. And I can run this code. Just got to remember what it's called. Make is number. Okay, it goes and compiles, and it's going to say 6 is a number. It's going to say that 7, which is a long, is a number. 3.14, which is a double, is a number. Now, notice up on the left-hand side with the int main, I'll pass some variables into these things. Okay? With those variables, Are they L values or R values? Why are they L values? Because they're named. Line 20, 1, 2, 3. Is that an L value or an R value? It's an R value. It will still work. Okay? It will still work. And so 1, 2, 3, which is an R value, is a number. The same applies with strings. Hello being passed in as an R value, world being passed in as an L value as a string, well, hello is not a number and world is not a number. So type traits are quite powerful. They tell us properties of what we're dealing with. Again, when we're building libraries and bits and pieces that we might not have written all the code in the program, they allow us maybe to do some error checking, but they allow us to do interesting things, okay? And so the standard template library has a huge number of predefined type traits. And I just got to load up this web page if it loads. Okay, and sort of do a search for type traits. Not type, yeah, that way around, not trait types. And we go to cppreference.com. And there's a huge number of them. Is void, is null pointer, is integral, is floating point, is array, is enum, so on and so forth. It goes even as far as figuring out if things are L value references, R value references. Comes down a little bit more. Figures out some stuff to do with are things trivially copyable. Okay? So if the type is trivial, it means that you can just do a direct copy of it on the compiler. Otherwise, you need copy constructor defined. You can test if something is signed or unsigned. And so on and so forth. I'm not going to go through all these, but there's a lot of stuff that you can do. Now, further down here, we start to get to some interesting ones. We can use is same to see if the type of two things are the same. But then we can start to modify types. And so we're going to go into this in a few minutes in detail, but we can add L value references, we can add R value references, we can add pointers, we can remove pointers from types. We can make things signed, make them unsigned. And so this type trait library is very powerful because it allows us to transform types in a similar way to how we would actually transform values. So when we're transforming values, we might add two values together, we might subtract two values together. That's the data contained, that's all the R values. But the types themselves we can modify. Again, we saw this a little bit on Thursday, was talking about metaprogramming. And we definitely got to take a look at this when we get to looking at custom iterators. Because has anyone thought about how an iterator actually works in the sense of, I can have an array of ints, I can have an array of doubles, I can have a vector of strings. And for all those types, I can do, say, a range-based for loop over it. So I can just do auto, if, colon, whatever the type is. Or I can do whatever the container is, dot begin, dot end. So everyone thought about how those things store different types, like the containers store different types, or the containers themselves are different in how they behave. Has anyone actually thought about how the templates and the STL and the compiler just knows that these things are iterators and just knows how to iterate over things? The way in which it does it is using type traits. And so that's what we're going to work through, is how these type traits work. And then when we come to Thursday, we're going to show you how to use the type traits to create an iterator class that behaves alongside any other type. And that means that this iterator class that we define will have to have certain properties. It has to adhere to certain properties because that's what makes it an iterator. It's not an iterator just because I name my class iterator. And that's not what makes an iterator. What makes the class that we'll define on Thursday an iterator is because it will have certain properties that the STL is able to use to go, oh yes, that matches the iterator type requirements. Okay? And we'll talk about that when we come to Thursday. But in the meantime, let's keep looking at the type trait library that's defined within VSTL. So this type trait library, as you probably can see, is a lot of it was defined in C++11 and C++14. Before that, parts of it existed in Boost and other libraries off to the side, but this has all been standardized now. Decal type, which we've already had a very brief look at, uses the type trait library to go and figure out what the type of something is. Decal type is not magic. It might appear to be magic where you get to do cool things doing a live demo on the lecture slides, but there is a certain degree of reasoning behind it, which is using all the type traits. And so decal type, so figure out what the type of this value is. Say if it's got the expression E inside it, okay? If E refers to a variable in the local or namespace scope, okay, so if it's in the local scope or namespace scope, or it's a static member, or it's a function parameter, then the type that's returned by decal type is the same type as that variable or parameter. However, if the E is not in that particular scope, but it's an L value, okay, so this might be from class scope, or it might be from one of other scoping rules that we've got, then it's a reference to that type. Okay? If it's an X value, okay, X values are expiring values. They're used in standard move. I'm not quite sure if you can see the very top of the screen, but we're going to actually get into detail about how standard move works the second part of today. But if it's an expiring variable, it's something that's about to go out of memory, okay? The result is an R value reference. And if it's neither an L value or an expiring value, that would make it a pure R value, so a PR value, and therefore the result is whatever the type is. So the rules for decal type are quite complex, okay? But it's, again, very powerful. So if we create int I, const j, which is a reference to I, actually it should be const int and j, we can create a pointer, and we can just create an undeclared, undefined type k, as in it's not initialized at this point. Decal type of I is an L value, therefore int x. Okay, decal type I is the equivalent of saying int x. Okay, that's an int. Decal type j. J is not a variable. J is not a type in the way in which we talk about types. What is J? On line 2 up here, what is J? It's a reference. A reference is an alias. It's not strictly a type. So decal type J, so decal type on for reference, will generate us a reference itself to that value k. So look at this very carefully. Even though j is a reference to I, decal type j will create its reference and then assign the value of that reference to k being there. Okay? Decal type star p. This is going to also return a reference. It's not going to return a pointer. It's going to return a reference, because p is an L value. Okay? So again, pointer types are special. Okay? Decal type brackets, I brackets. This one, again, you should be able to interpret this stuff. This brackets I, this internal brackets, is getting the value of I, the local variable I, but then wrapping it in a temporary type because of the inner parentheses there. So that inner parentheses, now we've got a temporary type. That temporary type is is either expiring value or PR value. I'm not quite sure off the top of my head how it's interpreted. Okay? So that makes it, basically it makes it an L value, and therefore we get a reference, okay, based on these rules. Okay? So the brackets there has made it an L value, okay, and so therefore that wants a reference. So decal type's quite complex in how it works. And so we're going to play a little game, a little puzzle. I have a function here. I have a function that takes an iterator, start, and iterator end. I want to do something in this function. Maybe I want to find the minimum or the maximum value in this function. But basically what I want to return is the dereference of the iterator. Okay? Here's the problem. I am taking an iterator type. Remember, with an iterator type, when I dereference the iterator type, I will get either reference or a const reference or a value back. Okay? In this case, I want a reference. So this star BG, I want it to return a reference. What should the type of question mark, question mark, question mark be? Oh, I'm giving you too much information. You mean like that?
Yeah.
Yep.
Yeah.
It's complex. Okay, I shouldn't have revealed all the solution there. Okay, so you think it's a decal type of star BG?
Yeah.
Okay. Do you think it's going to work? Oh, okay, you've just seen the next slide, so obviously it doesn't.
Oh,
But-
didn't it?
No, no. You're on the right track. Okay, so what we've got, okay, this is annoying. So, oh, I've got a different computer here. I knew that. Let me see if I've got the code. I don't have the code. Okay, let's write this up very quickly. Okay. So this is template, type name, T, oh no, IT. Okay, question mark, FCN, brackets, IT begin, IT end, open. We're going to do some sort of loop, and then we're going to return star BEG. Okay, so that code up there is what we've got on the screen. Okay, and Simon's solution is to do this. Decal type star BEG.
Well, I said star IT. You can't.
You said star IT. Okay, well, okay. So you said star IT.
Yeah.
Can't dereference the type.
You can't do it.
Can't dereference the type.
Oh, whoops.
Okay. So that one's broken. Sorry? You just want to replace all that with auto. Okay, we're gonna. Oh, okay. So he's getting on there. Okay, I'm gonna hold you because you've got the answer. Okay. So, did anyone have decal type star IT? That's what I thought you'd said. Does anyone have this solution? Did anyone think about this one? Yeah, I'm getting there. Some of you guys have worked it out. That's okay. But did anyone?
Iterator type and double semicolon and the value type. I mean, get the value type member of the iterator.
Yeah. This is complex. This is the short version. Right. Did anyone? I'm going to come back to you two who have kind of worked it out. Okay. Did anyone think about doing this? Why doesn't this work? So let's go back a step. This definitely doesn't work, okay? Because you can't dereference a type like that. Why can't you do this? Why can't you dereference that?
It's out of the scope.
Why is it out of scope?
The return type can catch the name of the beginning.
Yeah. So BEG isn't defined until later on. Okay. So this here, trying to dereference something isn't defined, not going to work. Okay. So trading return type is our friend here. Auto into there. Okay, this is hopefully what you guys were going to say. Is that what you guys were going to say? Do that? Yep. That was what you were going to say? Yep. So, we solve the problem with order return type, okay? So, a function takes in a type IT, returns a star BEG. We can use decal type to work out what the type of this is, but we can't do that until after it's been declared. And so search for trading return type and decal type combination help us out. And again, decal type using the type traits works out what that type is. Now let's go one step further. Okay, hopefully no one saw the thing there. Let's go one step further. This decal type return type is returning a reference. Okay, this is returning a reference. I want to return a value. I want to remove a reference and I want to return a value. How do I do this? I'm going to pause you because you seem to know the answer. Is that okay? Yep. So how might I return the value rather than a reference? So the decal type in this case is giving me a reference. How might I return the value? Anyone got any idea? Let me jump back to our standard template library information about type traits. If we scroll down this big list, we have somewhere remove reference as a type trait. Yep. And so, if I jump to the next slide, we can do this. With the trading return type, we can say remove reference of whatever the type of decal type star big is, type. And this type name up the front is required because the type isn't actually known until compile time. Okay? So using this type trait library allows us to do interesting things and interesting modifications with types. So we've got a function here that does something. It might be find min, it might be find max, and we want a copy of the data. We don't want it for reference to the data. We want a copy of the data. And so that's how we'd go and write that. People following so far? Yep.
What if you just return a constant reference?
Well, constant reference is still a reference. It's not a value.
And you could like deref, but you could make it non-constant and modify it if you really wanted to.
Right.
That's true as well. Yes, you could cast off.
You could
Yeah,
never do that.
you're definitely right. So the point was, someone said, can you just return a constant reference? Well, constant reference, you're still returning by reference, you're not returning by value, as you correctly point out. If you return a const reference, I can just const cast, and I can then go and modify your underlying data type. Okay? Returning by value, I can't do that. Okay? So as we've just seen on the web page, there is a lot of type transformations that we can do. Okay? And basically, these are type traits in a similar way to the examples we saw higher up. There's sort of two versions of each of them. So remove reference, if you call remove reference on something that's not a reference, it just returns the same type. Okay? If you call return reference on either an L value or an R value reference, then it removes reference correctly from it. Adding something as const, if something's already const, then it can't be const, so it stays how it is. Adding L value and R value references are slightly different because if something's already a reference, it has to stay in the form of a reference that it originally is, because references are special like that. Okay? But you can convert references to pointers. You don't have a pointer to a reference, you have a pointer to the thing that was being referenced. Okay? You make something signed, and so on and so forth. You can do things with removing the type from the array types like that as well. And so this is how remove reference might work. I'm not going to go into too much detail of how this code works, but we basically have a function up here called isSame. IsSame also uses for type traits. There's a type trait called isSame. It passes in two types and sees are they the same type. And so what we can do is we can use print same to say is an int and int the same type? Yep, that is. Is an int and a reference to an int the same type? No, it's not, so it returns false. And so on and so forth. We can then use remove reference to say is an int, and an int with its reference removed the same type. Well, an int with its reference removed is the same type because removing a reference from something that isn't a reference to start with is just going to stay the same. Okay, so an int and an int that has its reference removed is the same. Int and remove reference from L value reference. It's going to be true because the reference will be removed. With an R value reference, again, it's going to be removed. And a constant to a const int with its reference removed is still true. And so the point of this last one is you can actually remove a reference from something that's const. Because again, you're not modifying that thing there, you're getting a new data type out. Okay, so that bottom one is different from a const cast. Const cast allows you to go and cast off the const of a particular value. This remove reference is returning a new type. Okay? We can do the same with adding references. I'm not going to go into details about how this works, but again, you can see, or you can play with this later on in your own time. So, take-home message is the type trait library is very powerful for being able to modify and deal with types, particularly in templates. Okay? So, this then actually, yeah, sorry.
With the type traits,
Yep.
are the things that you reference out of the result always value or type? Like the constant thing that you operate on? The return thing from a type trait call,
Yeah.
is it you're always accessing the value parameter or the value constant or the type constant?
I don't quite understand what you're asking.
Like in the previous slide, if you're looking at the value, so you're printing off the value of when you call is same.
So it's same as taking in
Those two types.
those two types. It's same as a struct or a class.
Yeah.
And so this is the value of in.
So are they all called value if you want to use a type trait struct thing?
Go take a look at the standard template library. Okay, so the question is, are these things always
Called value.
called value? They probably are, or something similar to that. Okay?
Right. But
And
you have to look at it in a case by case basis.
you have to look at it on a case-by-case value, case-by-case basis. Okay? And also on the cppreference.com, it actually gives you possible compiler-based implementations of how these things actually look. Okay? So this thing's actually inheriting from a thing called a standard false or standard true type. And standard true type has a thing called type or value type like that. And again, possible implementations of how these things work. This starts to get really quite complex pretty quickly. Okay? But you can see the examples of how they're calling value and stuff like that. Okay? cppreference.com I showed you the other day is really good for just being able to see how all these things work. Okay. So we're going to talk about a thing called binding and type binding. And so we're going to put type traits off to one side for a minute and come back to these things. Okay? But remember we've got different types of values. So we've got R values, we've got const R values, L values, and const L values. And then we have 4 different types of references. An R value reference, a const R value reference, an L value reference, and a const L value reference. And depending on the parameter binding rules, depends on whether the R values and L values can talk to each of these reference types. Okay? And it probably makes sense that an R value reference can talk to an R value, because otherwise it wouldn't make sense for that thing to be called an R value reference. It probably makes sense that a const R value reference can talk to a const R value, and it can also talk to a non-const R value, because remember, the references themselves can be const even if the underlying data type's are not. So a const reference just means that if you're accessing it through that reference, you can't modify the values. But these R value references can't talk to L value references. An L value reference can only talk to another L value. An L value reference cannot talk to a const L value because the constant is at this low level, not this high level at this point. And the L values here can't talk to the R values at all. Now with const L value references, they can talk to everything. And this is why we use them all the time. This is why when we're doing copy constructors, not move constructors, when we're doing copy constructors, we pass in a const L value reference in. This is why when we're dealing with, say, trying to create a bind object to find if a value is greater than a certain value, we'll take that value in as a const L value reference. Okay? But the reason why we're pausing on this is because these R value references, so the T and ANDs, they bind only to non-const R values. This is an important thing to remember for now. So these R value references only bind to non-const R values, okay? And they're the values that we typically move from. Now, we're going to talk about standard move, probably at about 1 o'clock, okay? But we're working towards how does standard move actually work. But first of all, let's, again, focus a little bit just on the binding rules for normal L values. Imagine I've got this set up here, okay? I have a function foo, takes in a const reference, a const L value reference to a standard string. Okay, it doesn't do anything, but it takes in a const L value reference to a standard string. Into this function, I can pass L values, const R values, L values, and const L values, and you should be able to recognize the difference between them. C++, just like that, is an R value, because it's just a value, it's an unnamed type. This do function returns a const standard string. Therefore, it's a const R value, because it's still a temporary. This string J here is an L value, because it's a local variable on that left-hand side there. And of course, we've got the const L value there. All four of those types go and happily talk to this const type up here. If this wasn't const, half this code wouldn't compile. If it wasn't a reference, half that code wouldn't compile. And I may have an example of that, or not. No, I don't. So I don't have that example. I thought I did. Or maybe I do. Hold on. Oh, that's fine. It's the next one. Here you go. Const reference binding. Okay, so I do have this source code for this. Okay. So just to show you this actually works, I'll just go and compile G++ const reference binding, and it goes and compiles. Okay. And it doesn't output anything because it's not that exciting. But if I remove const from this, okay, now it doesn't compile. It can't compile because C++, being an R value there, it can't do that transition because it's not const. If I make it const again, and say now make it like that, so it's an R value reference, okay. Let's go clear that. Now it still doesn't compile because you can't actually have a const R value like that. So let's go try to create that one. Nope, that one doesn't compile either, so it doesn't like me. Okay? That's okay for it not to like me. The short version is that needs to be, it needs to look like that for that to work. Doesn't look like that, this code will not work. So const L value references bind to everything. However, when we're working with templates, we've got a special type of R value references, which are template R value references. These things are magic. They bind to everything. So if we, instead of having this foo function, we have this foo function as being a template. Okay, here it is. We have this template here. It's taking a template ampersand ampersand. This binds to everything like our const normal L value types bind to everything. This is what makes standard move work. Because remember, standard move, we need to move into something we can steal the data from. We can't do that. We can't steal data with something that's const. Okay? And how it does this thing, this template T ampersand ampersand, does a thing called reference collapsing. This reference collapsing uses bits and pieces of the template trait library to go and modify its argument to make it work. And so imagine this function foo, which is now this templated function foo. Okay, so it's taking in type name T and T ampersand ampersand. Okay. Now there's a couple of things to note straight away. I'm going to actually talk to this right-hand screen for a few minutes. This right-hand screen here with these different versions of R values, const R values, L values, and const L values, because this function up the top is a template, we actually end up with 4 versions of it. The non-templated version that we just saw over here, we've only got 1 version of that function. Okay, because it's not a template, we've only got 1 version. This one here, we've got 4 versions that get instantiated. Okay? Now, keep that in the back of your mind. Let's go back over to the left-hand screen. So the left-hand screen says parameter B it gets passed into foo. Okay, whatever that parameter B is. If it's an L value, or a const L value, but if it's an L value of type ampersand, sorry, not type ampersand, type A, then for type deduced is a reference, an L value reference to that type. Okay? So if argument coming in is an L value, then it gets deduced to be a reference, just a standard L value reference of depending if it's const or not const. Okay, so that means these bottom 2 on Permatrix right-hand side. This this int j equals 1 here, passing foo into j. Okay, that creates a version that's just foo in ampersand like that. On the line below, whereabouts this is a const reference. Okay, this is still at this point an L value because it's still a named type basically. Okay, so this is now going to create an instantiation that takes in const and ampersands. Okay, so this is the easy part. The next part says if there are values. If there are values, which again, R values are just values, they're not named left-hand types, okay? Then type T is just an A. So if the type's deduced to be A, rather than ampersand, A ampersand like that, the argument type becomes const ampersand, ampersand, like that. And so if you look back up on this right-hand side again, foo just with value 1 creates int ampersand ampersand. Foo with goo, and goo up here is just returning a const int, and again this is going to be an R value because it's not named. Okay, instantiates the const version of this. Now I'm surprised that nobody at this point has put up their hand and go, why do I care? I know some of you guys have done this before, okay? Really surprised that nobody at this point has put up their hand asking why do we care. As we approach the break, I'm actually going to give you a problem to solve over the break that you will not be able to solve without using these templated R value references. Okay, here it is. So I want you to take in 2 templated values by reference. I want you to increment the value and print them. And what this means is because I'm taking this in by value, because I want you to increment them, because they're coming in by value, what happens back inside main also needs to be incremented. Now remember when I do this with R values, I can't really increment an R value because it's a temporary type. It, for reference, doesn't make sense. But don't worry, with the templated R value references, this will work. Okay. But so the body of a function will look like this: template, type name T1, T2. Okay. Void add and print. You've got to work out what goes inside here. And I want basic code to be plus plus T1 plus plus T2. And the following code can be used to test the method. Create two L values, A and B. Inside main, print out the values of A and B, then add and print them. And then print out what A and B is back in main. And then add and print 1 being an R value and B still being an L value. And then add and print 2 and 200. And this is what the output should be. So we're going to take a 5 or 10 minute break. For you guys playing along at home, do this over a break and see if you can figure out the solution to it. Hopefully it should be pretty straightforward to work out if my explanation's been alright. Okay? We'll resume in 5 minutes. Okay, so who's worked it out? Anyone worked it out? Should be easy. Anyone wrote the code and worked it out? Okay, so let's step through all the answers that are wrong. Okay, it's always good to figure out what went wrong, and then we'll get to the right answer. So the wrong solution, of course, is if we just put in T1 and T2 like that. Why is this wrong? No, the slide gives it away, but why is this wrong? It's wrong because it's called by value, and I asked you to do call by reference. And so because this is called by value, not called by reference, inside the function it actually works correctly. But back in main, it doesn't work. So this add and print, well, it did the print correct, it did the add correct inside the function, but because it was called by value, it didn't work because it wasn't a reference. So that's wrong. What about just making these things references? Make it call by reference. What could possibly go wrong then? Clearly a lot, because that was the output for my compiler. Okay? So just making those things a reference isn't the right thing to do. I didn't actually put this up, but what if I put the word const in front of that? Will that fix my problem? Because the error right here says it's a non-const reference. So maybe I just put const in front of there and it'll work. Why won't putting const in front of there work? Pardon? Because I'm trying to increment the value. So yes, const is definitely not going to work. So sometimes your compiler is very helpful, and sometimes your compiler is not helpful at all, because your compiler is saying, oh, well, this is non-const. Let's just go make this thing const. Okay? So sometimes the compiler information is helpful, and sometimes that actually just leads you off down the wrong road. You might find that with assignment 3. Be prepared with assignment 3 to get pages of errors. Okay? So the solution, given what we've been talking about, is pretty easy. Just T, ampersand, ampersand, and everybody is happy. Okay? And this works because of reference collapsing and because of the rules that we've been talking about. So we're now going to look at the idea of a thing called standard forward. And standard forward preserves the types and the constantness of what we're passing around between functions. So without R value references, lots of things will just get automatically converted up to an L value. Okay? With perfect forwarding, L values stay as L values, R values stay as R values, and constantness is preserved. And the template for kind of how that works kind of looks a bit like that. Okay? You don't need to necessarily care about how these things work other than standard forward returns an R value reference, in order to do that, what it gets passed in is it removes the reference from the type, but then converts that removed reference into an L value, and then does a static cast of that L value off to an R value to do the return. Forget about how that works. It's just magic. You can pretend that one's magic. Okay? But this standard forward template is equivalent to 4 different versions, depending on things, L values, const references, and so on and so forth. Okay? But this standard forward, what it's doing is it's relying on type traits. It's relying on this remove reference type trait to pass the correct thing into our functions to preserve their types and their properties of their types. And why do you do this? I'm actually going to start halfway down this line because I've just told you most of this, okay? It avoids unnecessarily copying data, so it's faster, and avoids having to write multiple overloads for different combinations of L value and R value references. So again, the standard forward is very powerful for helping us out. Helps make our code run fast. And fast code is good code. So here's an example, and I think I have this one up on the screens. No, I don't. But I definitely have this one in the example files. Or maybe I don't. That's weird. This one should be in the examples. Why is it not? Perfect forwarding example. Okay, so this one's I've got on my screen. It's not in the sample code. I'll add it to the sample code. But this perfect forwarding example here, I have 2 functions. Well, actually, one function they're overloaded, and the function is called overloaded. One version of this function takes in an L value reference, just takes in the standard reference that we've been looking at all the time. The second version of this function takes in an R value. Okay? We have a templated function which takes in an R value reference that we'll call overload, or overloaded, just on X. And the second one we'll use this thing called standard forward. When we call overload on X, it's always going to convert this to an L value, and this top function, this top void overload, is always going to be called. Because the way, basically, the compiler underneath works and the types work and stuff like that. But using standard forward up here, preserving the constness, preserving the type correctly, we'll call this overloaded function to print out L value if it is an R value. And so what we can do is we can go into our main function. Okay, both screens have got the same code in them. And so we can create a thing called int a. Okay, I'm just going to assume it's default initialized to 0. And so if I just call a, foo a is an L value. A is an L value. So what happens is comes in this for our value reference up here. A becomes X now, but remember this is an L value down here. And so therefore the L value always gets called there. And then I standard forward, and because this is an L value coming in, then it will be an L value still there. So the output calling foo without an L value is L value, L value. So let's look at what happens when we do this with an R value. So instead of having a named variable a, we just call foo0. Okay? So we're passing in exactly the same value. So let's be clear here. Int a had for R value 0. Okay? So we passed it in 0. We passed it in by reference, by R value reference, okay? But because it was an L value, both times that L value function got called. The second time, this is now an R value. And so we call foo with the R value, overload X gets called and converts that off to an L value, first time round. Using standard forward to correctly preserve the type, on the second time that overload is called, it prints out R value, which is correctly what it is. And so you can see down here on the output, first time gets called, it says it's an L value because it loses that type that it had, or that constraint, that property it had. And then the second time, using standard forward, preserved that L value, R value type, it preserved the constants, and so it prints out R value, yes.
So does X become an L value because it's named? Like it's coming in, it's called an R value. Like
Yep.
in food, X
Yep.
is an R value, and then it gets turned into an L value because it's named by X.
Yes.
And then forward T looks at what X was
Yes.
before this got called.
Yes. You're exactly right. Go back up to the implementation of it, back up here. It's exactly what you just described it doing. It's removing the reference, and then it's correctly adding the reference back on. What you just described there was actually basically the perfect way of describing that.
Oh, clearly.
Okay? Can you say it again so everyone can hear you? Because you did that better than I can describe it. Okay? So what happened was on line 19, foo 0 got called, and 0 is an R value. Foo up here is an R value reference. That's cool. It's still an R value. So X at this point is an R value. But, well, it's not an R value, actually. X at this point is an L value, R value reference, if that makes any sense. So X is an L value. It's a name type, or it's a name type. I'm just going to wave my hands, okay? But it's a name type to an R value reference. Gets a little bit confusing at this point, okay? But because of that, when it does the X up there, it calls the L value version. The standard forward goes to the base of what X is and goes, are you an L value, are you an R value, what are you doing? And that's how it works out for that one. Yep, off the back.
So if we call overload with standard move X instead of just X, we get the R value version.
If we called, okay, let's try it. So you want me to put standard move in like that on that screen? That's what you're asking me to do?
Because then it'd be an R value again.
I think that should be an R value. I think. One way to find out. Let's go and compile this. Okay, G++, standard equals C++ 11, PF example. Oops, I can't spell. It compiled. And you are correct. Well, you're all. So look what it did. So we called standard move. Let's go back to the code. So we replaced that X with standard move. It's kind of good because it kind of leads into the next one we're going to talk about. So that one's using standard move and the other one's using standard forward. And there's a difference between them. And using standard move there, even though you should never do that unless you're actually moving, what you've done is you've converted that L value out to an R value. And that's why it's been called at that point. The second time around, remember back on the screen, both these times before was an L value. Second time around, we've converted that R value reference to an R value, okay? And so that's why it's called R value twice there. But the standard forward, so see there's a real distinct, clear difference here. Without the standard move, everything got converted to an L value. With the standard move, suddenly everything got converted to an R value. With the standard forward, they preserved what they were. Okay, we're seeing the difference in behavior? Okay, that was a really good question because I was not prepared for that, and that went, okay. Okay, and so that actually leads us on perfectly. I'm going to pay you later on for, into understanding how standard move works. Okay? Standard move works by coming in, and the return type is actually removing the reference from T, but then the return type is an R value reference, so the ampersand. Move takes in that templated R value reference like that. And again, it returns a static cast over that figure. Ignore how that stuff works. Too complex, don't care. Okay? What you should care is that it returns an R value reference. So for the first 5 lines of this, I don't care. Too complex. That's magic. Okay? But then let's break down how this works for string S1 being C++ and string S2 just being actually nothing, because that will default initialize to nothing. So we can say S2 is equal to standard move, standard string C++11. So we can say S2 is equal to standard move over an R value. Okay, so that line 8 there is a standard move over an R value. The second time, on line 9, standard move S1, that's over an L value. So even though I just said I don't care about what this is actually doing, we actually are going to care, because the next 2 slides are going to break down exactly line by line how that type trait, or the type trait system, is working to make standard move work in this case. Okay, because the difference here is this R value is passed in here. Even though we're moving, we're stealing from it. It's an R value. It's sort of like a temporary variable that doesn't really, well, it exists in memory, but it sort of exists quite differently to how the L value on the stack exists. Whereabouts the standard move over the stack variable, this L value variable on the next line, we're stealing from a different piece of memory. And so let's break down how this works. So in the first case, let's take a look at S2 is equal to standard move, standard string, C++11. Okay, so this is our L value version. And we'll remember, just in the back of our minds, how that function there looks, because I don't have it on both screens. Actually, let's go get it on both screens just to make it nicer. Okay, so I'm going to load up the second set of lecture slides on the second screen. Why did that load up there? Oops. Okay. I don't want to print it, I want to display it. Nope. There we go. And we're down here. Yeah, that doesn't work. Okay, so we're way down at the back of here. Let me just get there. Okay, so we're going to keep this up on this screen, and we're going to keep working for this on this device. Great. Okay, so on line 1 of standard move, we say template type name T. Well, type name T is going to be a standard string. Okay? So type name T is going to be standard string, okay, because we're moving from that parameter we passed in, that gets deduced by the compiler. Then inside this, on line 4, we're saying, no, sorry, let's keep going how the compiler actually does it. We get to line 2. Remove reference T. Remove reference T. Remove the reference in standard string, still therefore standard string. Okay? So therefore the return type is standard string R value. So R value reference, ampersand, ampersand. Okay, so remove the reference, got that type and turned it into an R value reference. Now, I'll just pause for 2 seconds. It's really important. You see how, even though it says colon, colon, type, ampersand, ampersand, do not put a space between type and ampersand, ampersand there. Floating ampersands in the middle of nowhere are really confusing, because I don't know, unless I look at this more closely, if that's meant to be an R value reference, or if I've got a space there, is that just meant to be an ampersand in the sense of like an and, like inside an expression or a statement or something like that. Okay? So ampersands just floating around by themselves is a style thing. It will compile. The compiler doesn't care about white space mostly. It will just take out the white space, but for readability for our code, that ampersand being on the end of there is important. Okay? Now, as we continue down, we get down to line 3 of how standard move works. It takes in an argument of standard string ampersand ampersand. Okay? Inside standard move, now it does a static cast of the same thing that we moved the reference from before. Okay, so we say static cast string ampersand ampersand t. Where t was the variable name of what was being passed in. That instantiates the whole function as being standard ampersand ampersand move, standard string ampersand ampersand t. So this line 6, this is what the function prototype from this whole template setup gets deduced to. And this is equivalent of just calling this function. Standard static cast, standard string, R value reference, R value being passed in. That is what all of that template gets deduced down to by the compiler. Who thinks it's easier just to write standard move and let the compiler deal with it yourself? Okay? So basically, these library functions are powerful. They do some stuff and we're sit there scratching our heads literally for a couple of hours just to figure out how to do this. Okay? Now let's take a look at the version that's using an L value. So that previous one was an R value. Let's look at the L value version. The difference between this one is before we just had for R value and therefore it was a standard string. The second time through is an L value, and so the deduced type is a reference. Therefore, when we remove a reference, we get back to a standard string. The return type's the same as before. For argument type though, for move, so the argument parameter coming in, is now just an L value reference. Well, sorry, it's an R value reference to an L value reference. Okay? So this gets reference collapse. So this is why we were talking before about reference collapsing and why remove reference is important for sorting out these things, because suddenly we've got an R value reference to an L value reference. And I'm scratching my head going, that's even hard to say. Okay? And so this remove reference, this reference collapsing is important to get the argument right. Okay? And so therefore our parameter coming in, sorry, for body of a function, we'll get to the parameter in a second, but body of a function looks like standard static cast ampersand ampersand t like that, which should be the same as the previous slide is. Okay, so that line there and that line there are the same. But the function body, so function prototype and also function body, but function prototype look different. So previous one, see the ampersand there, and for ampersand here, that's the difference between these two, one being for L value version, one being for R value version. The return types in this case are the same. Okay, so the type traits have been able to sort us out to get to the same version. And so this one, the equivalent function call, looks like this: static cast string ampersand ampersand S1. Oops. That bit's the same, but see what's being passed in is different. Okay. Again, technical details. It's called advanced C++ for a reason. Okay. What's the take-home message from this? The take-home message is not you should be able to go codeless. I'd love it if you could. But I'll be honest, I couldn't go codeless. Okay? Couple of take-home messages. Standard move is powerful. Standard forward is powerful. They help us with performance. They help us preserve the right types and right forms of things. You should know how to read code that has a call to standard forward inside it. So, big hint for the exam. This isn't the exact question, but you'll get a question that looks very, very, very similar to this in the exam. I don't actually think it's quite this complex off the top of my head. Okay, but you'll get a question that looks very, very, very similar to this in the exam. And the exam question will ask you to write what the output of this program is. Actually, I'm giving a huge amount away now. That is an exam question, actually. You have exam question. It's not this, okay, but it looks very, very similar to this, okay? That has maybe 20 lines of code like that, and the exam question is right about it. Okay? And the comments will be stripped. So the comments that say this is an L value and this is an R value, that will be stripped out, okay? Because that would be far too much of an easy exam question. Okay? But if you can answer these sort of questions for the exam, you are well on your way to an ASD. Okay? So this would be one of the hardest exam questions there is in the exam. Okay? So there's one final thing to look at briefly. We looked at variadic functions briefly 2 weeks ago. We looked at variadic functions in the tutorial last week. This variadic function that has a head and a tail and basically looks like a little bit of Haskell because it's just pumping a head and a tail off each other. What it does, because this is a template, it ends up going and creating a number of different instantiations to make this thing all work. Gotta say, don't care. I do care, you should know how this works, but this bit isn't that exciting. Okay, that's just the first bit of exciting bit of variadic templates. The more exciting version is using variadic templates with perfect forwarding to export all possible constructors of a member object at its parent's level. What does this mean? Well, let me jump back onto this right-hand side and go back to some code. Okay, let's go and create a new one. When we were creating the Euclidean vector class, some people came up with a very, very cool constructor. Okay, the reason I say it's a cool constructor is I suggest you might want to use a template. And the template might have taken in, let's just say type name IT, because I suggested it might take in a iterator. Okay, and Euclidean vector, and brackets IT begin, IT end. Okay. And the problem with templates that people are having on the second assignment, and I had in my own code, was that inside of this template, is suddenly I had to create all these different templated functions, I'd say non-templated functions for all the possible edge cases whereabouts I didn't want the templated one being called. Some people in their private variables had something like this. They had like vector double, this is called D, oh no, it's actually called values. Okay, so that's values in each of the dimensions. Now, my version of this code looked a bit like this. While begin not equal to end, values dot push back star BEG. And then in here I just say BEG++. Whose template looked like that? Yeah, about 10 people. Someone nicely pointed out to me that I could have just done that template like this. Values equals standard vector BEG end. And the reason why this works, is actually there's two different versions of vector constructor that, interesting enough, accidentally managed to match. So I could have called Euclidean vector with some sort of, say if it was this, L.begin, L.end, like that. I could have also called a Euclidean vector given a dimension of 4 and a value of 5 or something like that. Okay? Now it just happens that Euclidean vector has two overloaded constructors, one of which takes a start and end iterator, and the other one takes a start value and end value. And there you've gone and solved all the possible solutions that were required. By the way, this was an accident. This was an accident in the specification for assignment 2. But well done if you managed to achieve that. Okay? I'm going to now take this one step further with variadic templates. What I want to do with this perfect forwarding and these variadic templates is I want to create a constructor that can pass through all possible forms to the underlying object. Okay? So this one was lucky because actually, ironically and completely accidentally, there was two different ways in which you could end up calling the vectors overloaded constructor. But say I had a container or some sort of type that the number of arguments coming in varied, which is why you have variadic templates, because things vary. Okay? I want to create one templated constructor that can take all possible variations. I'm going to do this with standard forward. And it's going to look like this. Here is circle, triangle, square being passed into array. Here is a class called blob, which has a templated variadic function that does standard forward into the constructor of underscore v being a standard vector of type string. And so this first version, 10 C++11, 10 being an int, and C++ being some strings. Notice that this class isn't the thing that's templated. The template is actually on the constructor only, so member function template, okay? Variadic template being the type name ... args, okay? And so this will correctly use the vector's full constructor, even though this is an int and this is a string. The second one will use the vector's range constructor, because this is an iterator, and basically this is a pointer, and that's also a pointer. And so that will call the range constructor, and that way every single possible version of that vector's constructor I can export out. Basically what I'm doing is I'm revealing all the constructors available for that internal private data member out to my public interface on the class that's encapsulating it. It's pretty cool. It's pretty powerful. And because it's using standard forward, it correctly preserves all the data types and stuff like that. So we're using standard forward over a variadic type. So look at the forward here. There's args. There's args actually a variadic data type. So that's bringing together pretty nicely, actually, a number of things that we talked about over the last couple of weeks. We've talked about these type traits, these variadic functions. We've talked today about standard forward. We've talked about member functions. This, for 3 lines, actually, there's 2 lines of code, lines 8 and 9, brings together about 3 or 4 weeks worth of content. And you should be able to read that and understand what's going on. Now, I don't think there's an exam question on this particular piece of code, but if there was to be an exam question on this particular piece of code, the question would be along these lines. So it would be along the lines of, does this code compile? What else might it be? It might be, this doesn't have any output, but say this had some output, it might ask you what the output is. It actually might, again, here's a good exam question. Very simple exam question, but this might be a multi-choice one. How many constructors are generated? How many blob constructors are generated off this code? 1, 2, 3. There's 2. Okay, it should be easy. There's 2, right? Maybe a slightly harder question. There's 2 constructors generated off this code. What are the types that are passed into the first and second constructor? What I mean by that is, again, I'll just use the scrap code up here, okay? I'm definitely going to have a function, constructor called blob, okay? What for functions or parameters that go into this function here when this variadic type gets compiled out. What do you think the first version is going to be? Int. Yeah, it could be. It's got to be an int. It might be a reference. I wouldn't actually know off the top of my head, but I wouldn't care. So in an exam, I wouldn't actually strictly care at this point whether you get for int or int reference. But the first one's int. What's the second one? No. Char star. Actually, it's not just a char star. Const char star. Okay, so the first one is that. And the second one is what? What is the second constructor? Const char star star in both? Yeah, I think you're right. No. So I think we've got readings. Yes, okay, so we're basically done, unless anyone's got any questions. No questions? Okay, so on Thursday we're going to continue on and we're going to talk about custom iterators, which is important for your third assignment. Okay, see you on Thursday.